Right now, if you remember, we were covering the continuous time Fourier series representation, and the Fourier series of our interest is for a specific class of signals. They must be continuous time, first of all. We are not yet in the process of Fourier analyzing discrete time signals. We are analyzing continuous time signals, and they must be periodic. For periodic signals, we have a Fourier analysis, also known as the continuous time Fourier transform, or continuous time Fourier series, excuse me. And the series formula is already given in this box here. What does it say? It tells you that every periodic signal, x of t, can be represented as an infinite sum or a finite. Infinite also includes the finite case. Infinite sum of harmonics or complex sinusoids, which are in the form of e to the j times a frequency times t. And the frequency here is always in the form of k times omega 0. What was omega 0? Do you remember that? Omega 0 was the fundamental frequency of your periodic signal. So your first duty is to determine the fundamental frequency. Without knowing the fundamental frequency, you cannot proceed. Because the harmonics are in the integer multiples of that fundamental frequency. If the frequency is omega 0, then the other harmonics always appear at k times omega 0. And they will be the frequency of the harmonic. 2 times omega 0, 3 times omega 0. For those of you who have covered some power-related courses already, or for those of you who will see some power-related courses, you will see that for a rectangular waveform, for instance, if you have a rectangular waveform, the professor, the teacher will tell you that it has, it consists of harmonics like the fundamental frequency, which is 2 pi over the fundamental period. The fundamental period is one cycle of that. And the other harmonics are always at the odd multiples of k. For example, there will be 3 times omega 0. There will be 5 times omega 0, 7 times omega 0, etc. We will see that once we will learn how to determine these coefficients, AKs, which are some complex numbers, specific for this for a given periodic signal. We will see that example, and you will immediately understand or remember what it corresponds to in power line signals over there. Now this is a strong argument. The integer times omega 0 is a strong argument. And you must be careful about whether the signal that you come up with or you have is already periodic or not. For instance, here is an example. X of t is cosine 10t times cosine 8 pi t. And if you remember how to find the common period of these two periodic signals, it must correspond to the least common multiple of these two. And the least common multiple must be determined if only one of them is a ratio or a rational of the other. And we know that one of them has pi and the other one doesn't have a pi. And pi is irrational. So no matter how large a number you may multiply with pi, you will never get to an integer. On the other hand, 10 is, you will never get an integer number. And 10 is an integer number, so you will also multiply it with some other integers. They will not have a least common multiple. The least common multiple of the two frequencies are infinity in this case. So you don't have it. As a matter of fact, the period is infinity and the frequency is 0. And therefore, it is not periodic. You will not proceed with this thing. You may be confused about the fact that one of them is periodic, the other one is also periodic. So the first one has a period and a frequency, so it has some coefficients. The other one will also have some coefficients. What's wrong with it? The thing that is wrong with it is that there is no fundamental period, therefore you cannot assign a k number here, a k, which is an integer multiple of a fundamental frequency. You will not be able to therefore represent it as a Fourier series representation. It's impossible. For other signals, other normal periodic signals, of course, we will do that. Last week we started with some simple sinusoids, and the way to determine the Fourier series representation of sinusoids is simple. You have to just expand the cosines and sines using the Euler's formula, all right? And then, well, the representation is there. It's simple. Now, one other thing, or the rest of the topic goes on as follows. If x of t is not a sinusoid, or if it is not in a combination of cosines and sines and things like that, how shall we proceed? How can we find a formula to get ak here? A general formula for that. We will see that. And one final remark before finding the formula for ak. The frequency, the corresponding frequency of the harmonic is k times omega 0. And when a harmonic passes through a system, the system characteristics or the frequency response that you're looking at, the triangular shape, whatever, the low pass filters, the high pass filters, do you remember those? The frequency that will be passing will correspond to k times omega 0. That is the frequency of the harmonic. Now, let's see. Okay, so for this one, we don't have a solution because it's not periodic. Now, let's think of a system response example for this input-output relation. Y of t is equal to x of t minus 3. Now, this thing is a linear and time invariant system, interestingly, because it's in the form of a differential equation of 0th order. That's fine. It's almost trivial. What is the system? Can we give a name to this kind of an input-output relation? What system name would you recommend? Say it again. Delay. Yeah. This is a delay system. It is just delaying the input by 3 seconds and then giving the output. By the way, what is the impulse response of this delay system? H of t is delta t minus 3, because delta t is the thing that you need to apply, and it will also be delayed. So you have to make an analogy by thinking that if you convolve by delta t minus 3, if you convolve a signal by delta t minus 3, it shifts everything to the left. It delays everything. A delay system is an impulse response of delta t minus 3. Now, we will solve the question in two ways to find the response of this system to a periodic input, to a periodic simple input. The second way, I keep it as open, we will see that, but the first way that I will attack the problem is like this. Assume that you apply an input x of t like this, e to the j2t. This is a complex sinusoid with a cosine and a sine term. Complex magnitude. It's a sinusoidal oscillation. What is the frequency? The frequency is 2 radians per second. And what is the response of the system to this input? It is e to the j2 t minus 3, isn't it? And that is e to the minus 6j times e to the j2t. Now, do you remember the first input-output relation that we have seen? I told you that if a complex exponential, which is a sinusoid, if a sinusoid comes into an LTI system, then the output corresponds to the same signal, scaled. And it's the same signal, as you see. And this is the scale. E to the minus 6j is the scale, and e to the j2t also goes out without changing. But this e to the minus 6j is a specific amount of amplification, attenuation, whatever, a scale for this frequency only. If the input is e to the j 2t, if the input is in general e to the j omega t with a certain frequency omega, a parametric frequency omega, then y of t will be equal to e to the j omega t minus 3, right? And that is e to the minus j 3 omega times e to the j omega t. And this e to the j omega t is the input, the same at the output. E to the minus j 3 omega is the scale, more parametric for the frequency response. That is h of omega. Last week when I gave you some simple input-output relations, I said that I have to give you the shape of h of omega, the filter. It can be a low pass, a high pass, a band pass, whatever. But I have to give you. But for some simple questions like this, I don't really need to give you h of omega. Because by just looking at the input-output relation, you should be able to tell me what h of omega is. This is h of omega, and it is e to the minus j3 omega. Right? Now, if I ask you this question, since this thing is the frequency response, can you find the output of the system to any given periodic signal, not necessarily a complex exponential, e to the j omega t form? Suppose that the input is something graphical and it is periodic, like this, a rectangular pulse, like this, whatever. And the period here is t, and this is a. What is the response? How does it pass? Well, you can immediately say that it must be shifted towards left by an amount of 3. That's one way of attacking the same problem. The second way of attacking the problem, which is not very much recommended for such simple cases, but nevertheless you can do that, is this. If this is x of t, from x of t, you come up with ak, the frequency representation, the Fourier series coefficients. You just find it. Well, the method you still don't know, but you can find it. And then, from these AKs, by the way, it's a double-sided arrow in the notation. Usually, the left-hand side of the double arrow corresponds to the time domain, and the right-hand side corresponds to the frequency domain. So it's a Fourier pair, in other words, it's a pair. And from here, you say that the output y of t is paired to a new set of Fourier series coefficients, bk, which are equal to ak times h of the corresponding frequency. Now let's remember again, what is the corresponding frequency of ak for a certain k? Suppose k is 3, then what is the corresponding frequency of the third harmonic? It is 3 times omega 0. So in general you have to write it like this, k times omega 0. And by the way, omega 0 is equal to 2 pi over capital T. If capital T is the fundamental period, then the fundamental frequency is 2 pi over capital T. That is omega 0. So what you can do is you can, one by one, term by term, multiply the Fourier series coefficients, AKs, with the corresponding frequency response and see how they pass through that system. We are not going to do that because this one requires infinite number of AKs, so it's very impractical. Now, I told you that we have 2 ways to proceed, and the left-hand side was like this. The right-hand side was the formula for h of omega. Do you remember the formula for h of omega? I don't know if I can find it here. It may be, yeah, here it is. Right, here it is. In integral, h of tau e to the minus j omega tau d tau. Looks bad, but nevertheless. Let's try this formula now to determine h of omega. We have already discovered what h of omega is for this question. What was h of omega for this question? H of omega was e to the minus j 3 omega. Is it really that with that formula? Sorry. Let's see. Let's try at least. H of omega, since I know the formula, it's from minus infinity to infinity. Let me repeat it here. H of tau e to the minus j omega tau d tau. But taus are difficult to write, so I will write t. H of t e to the minus j omega t dt. This was the formula for h of omega. Let's see if we can find e to the minus 3j, 3 omega j, from here, from this formula. Let's verify. From minus infinity to infinity, h of t is delta t minus 3 e to the minus j omega t dt. Alright. Now notice that inside the integral we have an impulse which makes all the time values, t values, 0 other than t is equal to 3. At all other places it becomes 0. So when you multiply an impulse with something, only that certain point of something, that function, will be multiplied by this impulse, and all the others will be 0. What I mean is this. This will make the multiplication term, e to the minus j omega t, to be valid for t is equal to 3 only. For t is equal to other time instances, the impulse will be multiplying by 0. It will make a multiplication by 0. Do you understand that? What I mean is this. We can write the same expression like this. Delta t minus 3, which forces t to be equal to 3 only. Because it's valid, this impulse is valid only at t is equal to 3. It is 0 everywhere else. So I will write e to the minus j omega 3 dt. T is equal to 3. Okay? And since the only scaling factor is appearing at t is equal to 3, we will have an e to the minus j omega 3, which is independent from t, and therefore it can be taken out of the integral. E to the minus j omega 3 integral from minus infinity to infinity, a shifted impulse. And what is the area under the impulse? 1. So this portion will be equal to 1, and we will have e to the minus j 3 omega only, which is the same as this one. So using the formula, I came up with the same frequency response. I don't really like using that formula, the formula at the top right over there, of h of omega, because it requires some integration, and for some certain integrals it may be difficult to precisely evaluate what it corresponds to. But for simple functions like constant flat functions or impulses and things like that, they are manageable. So you can just find h of omega like this, if h of t can be found, or if h of t can be extracted from the input-output relation. I cannot guarantee any specific way of asking questions. I can ask you a question like this. I can give you h of omega as a low-pass, high-pass, whatever shape, and ask you what is the response. Or I can give you h of t, and then you have to use that formula at the top right to find h of omega, and then scale one by one the corresponding Fourier series coefficients, AKs. And you will call the new coefficients BKs, for example. Then you will combine those coefficients with the corresponding frequency harmonics to say that the output is y of t, which is a summation of, in this form. So y of t has Fourier series coefficients like this. So y of t is equal to summation k from minus infinity to infinity bk e to the minus j k omega 0 t. It's not minus, it's like this, plus. So what does that formula say? You have to combine the harmonics again. The past harmonics must be combined again to form y of t. So I can ask you like this. I can give you h of t and you have to derive h of omega. Or I can even give you an input-output relation, x of t versus y of t. And from there you first have to find h of t. And from that h of t you have to find h of omega. And from h of omega you have to find bk's, the transmitted Fourier series coefficients. Okay. Now let's try to find the formula for determining the Fourier series coefficients, AKs. I have to open a new page. So this is the representation. Once again, I'm writing it. AK e to the j k omega 0 t. From this expression, what is AK? Or you just have to manipulate both sides of the equation and then come up with an isolated AK. And that is the formula of AK, and AK will be in terms of x of t, of course. But what is that? How can we do that? This was a question that has been asked for the assistant entrance examination in my university. They asked the formula to derive AK in terms of xt. That was a question. And I remember that I was somehow magically able to solve that question, although after the third year, there was the fourth year. After the fourth year, we were getting that examination. So I was still remembering that formula. I wouldn't hope that I would remember, but I was remembering that. And the way to proceed from here is, well, you cannot do that if you don't know how to do it. All right? I mean, the proof is not a proof by some elementary methodologies. You have to know how to prove this. And the proof is as follows. You just first multiply both sides of the equation with this signal, e to the minus j n omega 0 t. Let's multiply both sides of the equation with that. Honestly speaking, I'm never going to ask you this proof or this derivation. But once you understand how such things are derived, it's very beneficial and inspiring. It's about algebraic inner products sort of things. I'm trying to make a methodology to extract one of the terms in the inner product by inner producing or inner multiplication with the other component. Like this. Okay, let's write this multiplication, e to the minus j n omega 0 t. Okay. So both sides of the equations are multiplied. And then I will integrate both sides of the equation using the same integral duration. So if these two functions are the same, then their integrals within some specific limits would also be the same. And that is equal to the same integral, k from minus infinity to infinity, ak e to the j, and I'm going to write k minus n omega 0 t. I have combined these two multiplication terms into a single exponent, dt. Now what is critical in terms of this integral is the limits. And the limits must be chosen as the fundamental period. of this exponential term. So it depends on omega 0. And the limits are from 0 to capital T, which is the period, or 2 pi over omega 0. That is one period of integration. X of t e to the minus j n omega 0 t dt is equal to, and since integration and summation are both linear operators, they can be interchanged. I can change their places. I will push the integral inside the summation, and outside it I will have this, and after then I will have the integral. It's not from minus infinity to infinity, excuse me. It's from 0 to capital T, of course, the same limits, like this. Now this, I'm sorry about the ugly handwriting here. Usually I don't write that ugly on the blackboard or things like that, but this screen is too small, and the inking here, the scripture, is not very accurate. That's why usually those things are a little bit bad. So summation ak integral from 0 to capital T e to the j k minus n omega 0 t. Now let's take a look at this thing, e to the j k minus n omega 0 t. When you integrate a periodic signal in one period, a periodic sinusoid in one period, what is the integral? Zero. In fact, this integral is always 0. It always gives us 0 because it contains cosines and sines. If k minus n is 1, then it's clearly one cycle. So in one period from 0 to capital T, one cycle integration will give you 0. What happens if k minus n is 2? Then it will have 2 oscillations from 0 to capital T, 2 oscillations. And the integral of 2 oscillations is again 0. If it is 3, again 0. If it is 100, again 0. It's always 0. If it is minus 2, minus 5, also one full cycle, 2 full cycles, or integer multiples of full cycles will appear, and therefore we will always get 0, except one case, when k minus n is equal to 0, which means when k is exactly equal to n, then e to the 0 is equal to 1, and the integration will not be equal to 0, it will be the integral of 1. So this thing, this integral is equal to something like this: 0 if k is different from n, therefore k minus n will be an integer, and it will be equal to the integral of 1 from 0 to capital T. What is that? T, capital T. It's equal to capital T when k is equal to n. So it's like a Kronecker delta, which forces k to be equal to n. For all other k's, when it is different from n, it gives you a 0. When during the summation index of k from minus infinity to infinity, it's always giving you, that integral is always giving me zeros. At only one instance, when k matches exactly n, then the integral will be capital T. And there, I will say that this one is equal to, therefore, the summation is always 0 except for one point, and that one point is when k is equal to n. an will be here times capital T. When k is equal to n, ak is an, and the integral is capital T. For the others, the integral is 0. And that is equal to this integral from 0 to capital T, x of t e to the minus j n omega 0 t dt. Now, we have already discovered the formula for ak. In fact, an with a different name, we found it. Therefore, an is equal to 1 over capital T integral from 0 to capital T xt e to the minus j n omega 0 t dt. And here is our famous formula for discovering the nth Fourier series coefficient. If you just replace n with k, it will correspond to the kth Fourier series coefficient, of course. That's the methodology. Now, this formula is, unfortunately, I have to say, more important than the way we derive it for the time being. You have to remember or memorize this formula. It's a very canonical, classical formula to represent the Fourier series coefficients, AKs. One thing that you have to notice always is that if you are having Fourier-related things, if it's a Fourier transform that you're looking for, this formula is more or less the same. I just said that. I don't remember whether I have written h of omega from h of t. And we just found it. So let's find it again. The formula for h of omega. Where was it? It was one page before. Yes, here it is. H of omega is integral ht e to the minus j omega t dt. Integral ht e to the minus j omega t dt. Here again, integral of xt e to the minus j omega t dt. But omega is n times omega 0. The frequency is n times omega 0. So whenever you are discovering the frequency version of a time signal, you just need to multiply it with e to the minus j omega t and then integrate. That is how you find the Fourier transform or the Fourier series or whatever. Okay, that's always the formula, with some exceptions, of course. This one is periodic, therefore it has to be, the integral is within one period only, from 0 to capital T. By the way, this 0 to capital T is not precisely important. The duration of the integral must be capital T. The duration is important. It doesn't matter where you start and wherever you start, you have to end it one period later. So it can be from minus capital T over 2 to plus capital T over 2, for example, the same duration. Okay, so the duration must be capital T, not necessarily from 0 to capital T. And it has to be normalized to capital T by multiplying with 1 over T as well. So this formula is a critical formula that from now on we will have to use to discover the Fourier series coefficients. And the first Fourier series coefficient example we will give after the break. Let's give a 15 minutes break. We will continue after this.